All right, welcome. Today we're going to demystify a piece of high school math that, believe it or not, secretly runs the world around us. Yeah, we're talking about that simple, elegant curve that shapes everything from a home run all the way to a giant suspension bridge. Okay, let's dive right in. I mean, this might seem like a totally random list, right? But they all share the exact same elegant, predictable curve. Think about it. The path of basketball takes to the hoop, that graceful arc of a bridge, even the shape of a dish pulling signals from space, they're all governed by the very same mathematical principle. How cool is that? And that shape, well, it's called a parabola. This is not just something you see in textbooks. It's a fundamental blueprint for how things move under gravity and how we build some of our most important structures. You could almost say it's nature's favorite curve for anything that gets thrown or launched. So, the language we use to actually describe this universal curve, that's the quadratic equation. You can think of this formula as the code, or the blueprint, that lets us precisely map out any parabola we see out there in the real world. All right, section 1, from graph to equation, the blueprint. So, if you can see the curve, how do you actually write its blueprint? Let's break down how we can turn that visual shape into a real working equation. The real beauty of parabolas is just how predictable they are. And the easiest way to pin one down, to define its equation, is by using its vertex. That main turning point, the lowest or highest part of the curve, and then just one other random point that the curve happens to pass through. That's all you need. And to do this, we've got this super handy template called the vertex form. Now, don't let the letters scare you. In this equation, h and k are just the x and y coordinates of that vertex. It's awesome because the formula has the most important point of the whole parabola built right into it. So turning a picture into an equation is basically like following a simple recipe. It's just a few steps. First, you pop in the vertex coordinates for h and k, then you use that other point we mentioned to solve for a. And a is just a number that tells you how wide or narrow the curve is. Once you've got a, boom, you have your final complete equation. It's a really clean four-step process. Okay, next up, cracking the quadratic code, the master key. So now that we have the equation, what do we do with it? How can we use it to find specific answers? Like, for example, if we have the equation for a thrown ball's path, how do we calculate exactly where it's going to land? And listen, if you ever struggled with this stuff in school, you are definitely not alone. The way it's often taught, usually through a process called completing the square, can feel super confusing and kind of random. So it is perfectly normal if it didn't click for you right away. So you know what? Let's just skip all the confusing parts and get right to the master key, the quadratic formula. This thing is the universal tool for solving any quadratic equation. Seriously, as long as you know your a, b, and c values, you just plug them in and it spits out the solution. What this formula does is let us solve the equation for what we call its roots, or zeros. And these are just the super important points where the parabola crosses the horizontal line, the x-axis. Where it hits the ground, so to speak. So for that ball we were talking about, the roots would tell us the exact landing spot. All right, moving on. Beyond a single point, the solution map. But what if we need more than just one or 2 points? What if we need to know about a whole range of possibilities? Well, questions like this one, questions that ask about a range, like above a certain height or below a certain depth, they require us to shift gears a little bit, from quadratic equations to quadratic inequalities. And this really gets to the heart of the difference. An equation that pinpoints a specific moment. For instance, exactly when does the ball hit the ground? But an inequality? That maps out an entire range. Like, for what period of time is the ball above the hoop? See the difference? Points versus ranges. So the process actually starts the same way. We find those roots using the quadratic formula. But for inequalities, these roots take on a new role. They become our boundaries. We start calling them critical numbers because they're critical. They divide our whole problem into different regions on a number line. And from there, we use this simple but really powerful tool called a sign chart. Think of it like a visual map. Once we mark our critical numbers on a line, we just pick a test number from each of those new regions. We plug it into our inequality and just check if the result is positive, which means our parabola is above the axis, or negative, meaning it's below. It's that simple. And this simple process creates our solution map. So let's say our critical numbers are -2 and 3. We test the regions on either side and in between them. The region that comes out positive, that's where our parabola is above the axis. So for that rocket question, when is it above 1,000 feet? We just find that positive interval on our chart and bam, there's our answer. Okay, last section, why this shape matters, the payoff. So let's circle all the way back to the beginning. We've seen how to write the equation for this curve, and we've seen how to solve it. But why? Why does understanding this one shape matter so much in the real world? Well, because it's everywhere. From engineering the strongest bridges to calculating the perfect arc for a satellite dish, all the way to helping businesses find that sweet spot for pricing to get the most profit, this is not just some abstract math. It's the hidden language that helps us predict, build, and optimize pretty much everything in the world around us. Look, what we've talked about today really just scratches the surface. But now you have the tools to see this universal curve everywhere you look. Seriously, from the water in a fountain to the path of a cliff diver, the parabola is all around us. And now you kind of know how to speak its language.